Okay, this is going to be the third video on Taylor polynomials. And if you haven't done it yet, I would definitely watch the first two videos. The first one was on how to find the Taylor polynomial for the sine. The second one was how to find the Taylor polynomial for the cosine. And in this video, we'll look at how to find a Taylor polynomial for e to the x. And we'll put a couple of restrictions on it. We'll have it centered at 0, just like the other ones. And in addition to finding the Taylor polynomial, we'll also want to identify the general term, and then finally we'll take a look at what the graphs look like. So it'll be the similar format to what those previous two videos were. So again, if you haven't done it, I would definitely watch the sine one first, the cosine one second one, and then here comes the third one. Okay, now, whenever you want to find a Taylor polynomial, the first thing to do is to start with the formula. And just to remind you, if you look in your book, you should find this definition for a Taylor polynomial. Now, this would be if it's centered at C. Now, there's a special case. If you center the polynomial at x equals 0, then a Taylor polynomial actually becomes a Maclaurin polynomial. And the only difference in the two is that if you center it at 0, that means C is the center. If C is equal to 0, start with the Taylor polynomial, and you'd have x minus 0. Well, x minus 0 squared just becomes x squared. So a Taylor polynomial turns into a Maclaurin polynomial. So just keep in mind, all a Maclaurin polynomial is a special case of a Taylor polynomial centered at 0. Now, since ours is actually centered in 0, the problem says find the Taylor polynomial, but in effect, we're really finding both of them at the same time since they're the same thing. But we'll use this formula for the Maclaurin polynomial because it's centered at 0. So when you start the problem, the first thing to do is to take this formula, and I would suggest just copy it down on your page, because it's really just a matter of filling stuff in. So here's what it looks like. Now again, I've put all the derivative information in blue, the factorial information in red, and then the power information in black. And we'll follow exactly the same steps we did before. So the steps to work on this would be the following. You need all this information on the derivatives. So the first step on any Taylor polynomial problem is actually just go ahead and find the derivatives. So we'll put our step over here, find the derivatives. And that's going to be the initial step. Now, the second step is going to be to evaluate the derivatives at 0, but just like in the first couple videos, I would suggest you put step 1 and step 2 right directly across from each other, because it'll make it easier to keep from skipping terms. So the first step is to find the derivative. Second step is to evaluate the derivative. So you want to evaluate the derivatives at x equals 0. So that's going to be the second step. So we'll go ahead and start on this. Now again, it's your choice how many terms you use. In this example, I think I'm going to go to the fifth one just because they're easier. And if you've watched the first two videos on sine and cosine, one of the things you'll notice about this is whenever you find the Taylor polynomial for e to the x, it's actually one of the easiest ones because the derivative of e to the x is e to the x. So it speeds things up a little bit. So the first thing you're going to need is this right here. You're going to need the original function. So we'll take f of x. And actually, I think I'll do all these in blue just because this is the blue part of it. So f of x is equal to, and the original function was e to the x. So there's f of x. Now I'll start getting derivatives. So I need the first derivative. So f prime of x. And again, what makes this so easy, the derivative of e to the x is e to the x. Makes it much easier. We'll get the second derivative. Second derivative is also e to the x. I'll get the third derivative. So f prime 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 of x is also equal to e to the x. Now at this point I'll switch to, and normally I've done this, rather than writing primes out forever, put parentheses 4. And what that means, that's the fourth derivative of x. It's also equal to e to the x. And in this problem, I'm going to go ahead and go out to a fifth term. So the fifth derivative of e to the x is also e to the x. So kind of an easy problem because they all turn out to be e to the x. Now the next thing to do is, now that you've got the derivatives, if you look at the formula, you need to take each of those derivatives and evaluate them at the center, which in this case is x is equal to 0. And again, by putting them horizontally, I just go straight across here, and you can do them right across like this. So you want to evaluate the original function. This one says evaluate the original function at 0. So just take a 0, plug it into this, and you get e to the 0 is equal to 1. So the original function evaluated at 0 is 1. And then do the same thing for this one. This one is also e to the 0 is equal to 1. And these are all easy because they're actually all the same thing. That's why this is one of the easiest functions. Take the second derivative evaluated at 0 is 1. The third derivative evaluated at 0 is 1. And again, each one of these is just coming straight across like this to right here. The fourth derivative evaluated at 0. So e to the 0 is 1. And finally, the fifth derivative, e to the 0 is 1. So finding the derivatives when you're working with e to the x is really pretty easy, especially if it's centered at 0. Okay, now what you want to do is to take all of these and begin to include them into the coefficients of the original thing. So we'll scoot this down just a little bit. And what I like to do here is to take this definition and rewrite it down here, because that way I won't leave things out. So what I'm going to do is actually just make a copy of it. So I'll grab this, and I'm just going to pull it down and put it right here and basically start all over again. So I'll scoot this down just a little bit. So now, as you run through the definition, you need the function evaluated at 0. All this blue part, or what is in this column right here, it turns out they're all equal to 1. So now we just begin to fill things in. So let's go ahead and do that. This is going to give you, the polynomial as p sub n of x. Now, for each of these coefficients, really just go up, and in this column right here, pull out what you need. So I need the original function evaluated at 0. Well, here's the original function evaluated at 0 is 1. So I'm going to have a 1 right there. Then I have a plus. Now, I need the first derivative evaluated at 0. Well, that's this one right here, which is 1 times, don't forget, times x. Then I need the second derivative at 0. Well, that's this term, which is that right there. It turns out all of them just happen to be 1. So that's going to be 1 divided by 2 factorial times, and we'll make this just be x squared, plus, now we get the third one. Again, they're all 1. So first of all, the third derivative is 1. So you've got a 1 there, divided by 3 factorial times x cubed, plus, now we'll go to the fourth one, which is also a 1, divided by 4 factorial times x to the 4th power. And then finally, for what we've done, the fifth derivative is also 1, divided by 5 factorial times x to the 5th. And it goes on, and there's some additional terms out here. Now, again, since this is a polynomial, it doesn't go on forever. We'll actually put a concluding term out here at the end. But I think I'm going to do this at this point. I'm going to simplify things just a little and make it look like this. This is going to be the polynomial, and I'll just rewrite it. It's going to be equal to, here's 1 plus x plus, and this one would be x squared over 2 factorial, then plus, this will be x cubed over 3 factorial, plus x to the 4th over 4 factorial, and for what we've done, plus x to the 5th over 5 factorial. So it looks like that, and then we're going to put plus. Now, what the problem said was this. I'm going to put a plus, plus 3 little dots here, and let's go back up to the original question. And what the original question said was, find the polynomial, which we've now done, but also identify the general term. Now, what the general term is this term way over here to the right. So right now you've got the fixed part of it, but you need to get this right here. So in terms of n, to show what the general term is. And this is what you've done earlier in the course, changing a polynomial into some sort of a general term. So what we'll have is this. I'm going to go ahead and put a fraction bar right here. And first of all, it's not alternating in sign. They're all positive, so I don't need to put a -1 to the n power here. And what will happen is this. Whenever you're doing this, a lot of times it helps if you do this. Go ahead and label the terms. Now, it starts at 0. So this is going to be n is equal to 0. This one is n is equal to 1. N is equal to 2. N is equal to 3, and so on. If you do this, it just makes it easier to find the pattern for. So what happens is in the numerator, it's just, notice that the exponent matches whatever the term is. So 3 matches 3. This would just be x to the n power. Then in the denominator, the same thing happens with the factorial. You've got actually 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. But notice the factorial matches the term, so it's just n factorial. So what this is right here, this is the general term. So that's going to be the general term. So at this point, you've got the polynomial, and you've also got the general term. Now, before we look at the graphs on these things, sometimes you'll see it in this form, is rather than leaving it in factorial form, there's some advantages to writing it out in actual numbers. So I'm going to go p to the n of x, and I'll change those factorials into numbers. So this is going to be 1 plus x squared. I'm going to do this rather than 2. 2 factorial is 2 times 1, which is just divided by 2. Then I've got a plus. Here's an x cubed. And divided by 3 factorial, that's 3 times 2 times 1, which would be 6. Then plus x to the 4th. 4 factorial would be 24. And then finally, we'll go ahead and put one more on here, x to the 5th, divided by 5 factorial, which would be 120, and then plus, and you go all the way out here to the end. So that's going to be a Taylor polynomial for e to the x. So it's going to give you an approximation for e to the x, depending on how many terms you pick. Now we're going to do exactly what we've done before. Let's scoot this thing up, and then we'll graph some different versions of this depending on how many terms you pick, and show how it affects the accuracy of the answer. So let's do this. We'll go ahead and I'll move this up out of the way where we can see the graph. And it'll look something like this. So we'll stop it about right here. Now the idea is this, suppose that I wanted to come in here, and we're just going to move it term by term. So suppose you decided to estimate this thing using just this one term. Right? So the idea, forget about all these x's. You just wanted to use this would be a 0-degree polynomial. And this would be a terrible way of doing it, but we'll go ahead and try it anyway. So if I do this, now the question is, I've got e, and how accurate can I get this answer? So I'm going to put a little question mark right here. E raised to what to give me an accurate answer? Okay, now to see that, this is the graph of e to the x right here. And we will go ahead and make it be, put y to the first power on. So if I ignore all these terms up here and just make the polynomial be y is equal to 1, I would get a graph that looks like this. So what happens, you just get a horizontal line that goes through 1. So we'll kind of zoom in here and see what this thing does. So when x is equal to 0, now again, the blue graph is the actual graph of e to the x. If you only used y is equal to 1, you would get the pink graph, and the idea is for the pink graph to approximate the blue graph. But the trouble is, this is a terrible approximation. Notice as soon as you move away from the center, which is x is equal to 0, the pink graph begins to separate from the blue graph. So this would be a terrible approximation. So let's see if we can't improve it just a little bit. We'll go up here and do the following. Rather than staying with one term, let's expand it to 2 terms. So let's pick up this. And this is going to be e raised to some power. So now what you've got is a 1 plus x. And let's see what that one looks like. So if we added that, we'll go to this and hit the graph. And now what you get is this yellow graph. And notice it's a 1 to the x, that's a linear equation, so this is going to be a straight line. So this is the model first-degree polynomial to model e to the x. But how good does it do? Well, again, let's zoom in and take a look here and see what's going on. Now, looking at the pink one was terrible from the beginning. So the question on this is, how far out can you go before the yellow graph begins to separate from the blue graph? And just looking at it, it looks like not very far. Once you get out to about here, x is equal to 0.2, you can clearly see that the yellow graph and the blue graph are beginning to separate. But inside there, the yellow graph does a pretty good job of modeling. So what this means is this. You can use a first degree, if you just wanted to use two terms, you can get out to about, it looks like about 0.2. So anything in here, the yellow graph does a pretty good job of modeling. But beyond 0.2, the yellow graph does a bad job. So the next thing to do is just add another term. So we'll come up here and we'll add 3 terms. And now we want to know, what does that do to affect it? So to graph it, let's go ahead and we'll just go ahead and put that second degree term in there. So I've got this. I'll hit the graph. And first let me do this. And now I'll go ahead and draw the graph on there. And now you get this. This would be all the way up through x squared. So this is going to be a second degree one. And it should improve the accuracy of the answer. So again, let's zoom in and see what it looks like. How far does it go before it begins to separate? So the yellow graph made it out to about 0.2. And just looking at this, the question is, where does this light blue graph begin to separate from this graph? So again, we'll kind of zoom in close here. And I'm going to guess that clearly they're separated here. So you go in and I'm just going to eyeball and say about 0.5. So if you use a x squared polynomial, you can get an accurate answer out to about e to the 0.5, about right in here. So let's go ahead and put that up there. So this would be e to about the 0.5, is about as accurate as you can get. Now, once you go beyond 0.5, the second order begins to separate and it begins to fail. So we'll just keep doing the same thing. Extend it out to another term. So we go from here over to here and we'll try a cubic term. Now how far can you go out? Well, again, let's go back. We'll reset the grid, and let's put the third order polynomial on. So it looks like this. We draw that graph. Okay, so this cubic one here is this red graph. And let's get in and see how close that one looks. So if we zoom in, now what you want to know is how far in can you go before the red graph begins to separate from the blue graph. So again, I'll zoom in a little bit and you can tell they're clearly separated up here. So I'll come down and it looks to me like, oh, maybe about 0.7, 0.8, something like that. Let's just say 0.7. So at 0.7, the red graph gives a pretty good approximation of the black graph. By 0.8, you can just begin to see a little separation in there. So this one looks like it could be good out to about 0.7. And we just keep doing the same thing. Let's reset the grid. This time let's go to a way over here to a fourth order one. So let's include these 4 terms, but not the fifth term. So now how far out will that one go? So again, let's go back to our graph. Let's get a fourth order one. And fourth order looks like this if we draw it. So this green graph is a 4th degree polynomial. And hopefully it's going to be a little better. The idea is every time you add a term, you should improve the accuracy of the answer. So let's zoom in and see how long the green one approximates it. So I get in here, clearly the green one and the blue one are separated from here, but it comes in and it looks to me like, oh, you might get out to about maybe 1. You can begin to see a little separation there. So let's call it 1. So this one looks like it could go out to about e to the first power. And finally, we've got one more to go, so let's just go ahead and do that. Suppose you took it and you decided to go with all 5 terms that we've got here. And let's see what that one does. So we'll zoom in, take a quick look at it. That's going to be this one. Draw it. So that's this orange graph here. So now I've got a 5th order one. And let's see how far out the orange one does a good job of modeling the e to the x. And we'll zoom kind of in here. Now the question is, where does this orange graph begin to separate from the blue graph. And clearly they're separated here. If we get in just a little bit closer, they're separated here. It looks to me like you could go down to about maybe 1.5. So the question is, where does the orange graph begin to separate from the blue graph? Seems to be somewhere around 1.5. So that means that this one could be good out to about 1.5. And then you just keep doing the same. You go out forever or to a fixed number of terms if it's a polynomial, and you get to pick the number of terms. And just in general, this is true. The more terms you pick, the more accurate the answer is going to be. But it's also true of this. Notice, as you get in close to 0, they're all fairly accurate, except for the pink one. As a matter of fact, let's do this. It's kind of interesting to zoom in and see what happens here. So I'm going to find out, suppose I wanted to know this, with x equal 1. Then if x is equal to 1, remember e to the first power is about 2.718. So let's take a look and zoom in and see what we come up with. So I'm going to zoom in, and as I get in close, just kind of watch. Now, the idea is, when do they begin to separate? The pink one is terrible from the beginning. So you get in a little closer. Now, as you get in closer, you can tell the linear one, the yellow one, the first order one, also is beginning to separate. So it's not a very good model from there on in. And again, right now, it looks like all the other ones seem to be a pretty good model, but let's just keep getting in closer. So as I zoom in, now this blue one, that's the squared term. It begins to separate. I zoom in closer. This red one is the cubic one. It begins to separate. But notice the last two are still pretty good. I zoom in even closer. Finally, the green one begins to separate. That's the fourth order one. Now, if I zoom in even closer, but look where I am. We'll go in a little bit more here. If I get in even closer, now finally, this orange one is the fifth order one, and it begins to separate. So for a fifth order term, that's about as accurate as I could get. Now, how accurate is the answer? Well, let's do this. A couple things here. Starting with this, if you look over here on the right-hand side, you've got about 2.7 and 2.72, and it's the exact answer, of course, would be about 2.718. So it seems to be pretty accurate. Let's get in just a little bit closer here. If I really get in tight, then the blue one is 2.718, and you can kind of see if you look down here in the left-hand corner, as I put the cursor on there, notice it says 2.718. So that's what should be close to as close as you can get to the exact answer with this graph. But how accurate? That orange graph is the fifth order graph. How accurate is it? Well, let's go down and put it on here. It gives you about 2.717, so it's accurate to within about 3 decimal places. So what you want to take from this is that if you zoom in, you can clearly see it, each one of the different powers distinguished. But as you zoom out, then each polynomial model blends back into the model, to the original, and let's just kind of do this as we go through here. So as I zoom back out, there goes the fifth order one blending back in. The green one is the fourth order, and if I keep zooming out, it blends back in. If I keep going out, the red one is the cubic, it blends back in. If I keep going out, the blue one is the squared, it blends back in. And then finally, the yellow one never does quite get there. So if you get out, and the pink one, of course, is horrible. So as you get pretty far away, it looks like any one of them work out fine. But as you get in close, you can see that they're different. And one last thing before we get out of, just a reminder. If you want to improve the accuracy of the answer, use more terms. So I go out to an x to the 7th, x to the 10th. Or another way of improving the accuracy of the answer is to take points that are closer to the center. So the closer you get to 0, all the graphs begin to look pretty good. But as you go way out here to the right, the graphs begin to separate, and here's where the different powers become important. So anyway, there's a quick look at how to find Taylor polynomials for e to the x.